Hello. We will wait for 2 minutes to see because people have not arrived yet. Okay, so we'll start now. It's already 6:05. Okay. So yeah. So this week's lecture contained the following topics. where uh, first of it was some examples of continuum limit. Examples of system where we take the continuum limit, and then uh, after looking at some of the examples, uh, we went into the variational approach, variational problems. Here, brachistochrone, brachistochrone, spelling maybe that, and Snell's the Fermat principle in optics, the Snell's law using variational approach was derived. And then we went onto a very important topic called symmetries of the sum and other theorem. We discussed some examples like angular momentum in a rotationally symmetric system. L is for angular momentum, and also the LRL vector in case of central forces. In the end, we discussed some symmetries in field theory. These were the topics that were discussed, and I will start with a problem. I'll start with the problem 1, and I'll start the problem actually of the last class, which I actually forgot to uh, mention to you guys, is that we use Lagrange multipliers to solve the constraint problem. This was not done in the last class. In the last class, there was direct substitution of the constraint equations. And this it was done in a different way, and we'll learn a new technique this time. So the problem which I have is taken from the instructor's book, and it is problem number 17 of dynamics of classical and quantum fields by Girish Satlu. And yeah, so the problem we have is that we have to use Lagrange multipliers to solve a particle constrained to move along a sphere in the presence of gravity. And how should the multiplier be used in the Lagrangian approach? We just have to find the equation of motion. Suppose we have got a sphere and there's a particle here. There is a ball, suppose, of mass m, and it is constrained to move in the surface of the sphere. And now, so hello, can you hear me? Hello. Yeah. Yeah. So just tell me if you can hear me. These were the topics. These are the topics whose problems I'm going to discuss in this class. These are the topics of the lecture 5, 6, 7, 8 of uh, the uh, of the videos. And I'm going to actually start from this. I'm doing a problem. The problem is the question number 17 of the book, instructor's book. Okay. And this problem, how to do it using Lagrange multipliers, I had not discussed in the last session. So I'm going to discuss it now. So you've got a mass m, which is constrained to move on a sphere. And you have to solve this via using the Lagrange multiplier method. You just need to figure out the equation of motion. That's the question. All right. So let us start. The Lagrangian should be half m b square. And in this case, it is r dot square plus r square. This is the and here some angle. This is r dot square plus r square theta dot square plus I square sine square theta phi dot square. And here, so this will be the Lagrangian of the free particle in spherical polar coordinates. And we have the constraint. Suppose this is, say, R. Then our constraint is R is equal to R, capital R. Okay. Therefore, using Lagrange multiplier is some variable, say lambda. I'm going to incorporate this in the Lagrangian, and it will be incorporated like this. Remember, the small r here is also, you have to treat this as what do you say, mm, a degree of freedom, because you're solving it in a different method here. Uh, Now you take you do your this thing, variation. This will give you this will give you theta dot theta dot square equal ddt r double dot sorry, plus lambda is equal to r theta double dot. You have the equation for theta. The equation for theta is r sin theta cos theta lambda square is equal to r square sin square theta is sin theta cos theta dot square is equal to when we cancel r square is also cancelled within here is equal to theta double dot. And the third equation is just The third equation is theta dot ddt is theta is equal to 0. These are the equation of motion, and is equal to r double dot minus square. Okay, this is the equation of motion. Now, what you're going to do is, and also, yeah, this is the equation of motion for r, theta, and phi. Now we are going to find it for lambda. Equation for lambda. In that case, is just r is equal to r. Now you are going to plug this into this equation, and then you are going to solve it. There is a constant, so you have minus r squared, and yeah, the equation, the other equations, they pretty much remain the same. Mm. Yeah, now the thing to note here is that if you are going to solve this, these are the equation of motion. If you are going to solve this using the uh, using Newtonian mechanics, you would find that somehow lambda is related to the lambda is related to yeah, oh, I'm sorry, there's a potential term too. This is minus mg uh, r. So this is a zero in the potential mg r cos theta. So okay, this is not exactly problem 17. So we have not incorporated this term here. There's no gravity. So this is just a three particle, but this is how to do the problem. And if you are to do it using the same method, you would find that lambda is somehow related to the normal force. So if you're going to do it using Newtonian mechanics, you're going to find that n is somehow related to lambda. So this is a problem. Yeah. Now we are going to do, this is how you have to use constraints while solving problems. Now what we are going to do is we are going to solve a problem which is in variational principles, and the problem is number 13 in instructor's book. The problem is such that there is a cylindrical medium. There is a cylindrical medium, and this has got some refractive index, and speed of light changes in a smooth fashion with respect to the radial coordinate, and it changes as this. and n is constant, and yeah, a is the radius of the cylinder. Now we have to find the path of the beam. So that means this r should we should find a function r which satisfies the Fermat's principle of least Fermat's principle, and it should be a function of theta. So that's all. So what we want to do in this problem is we want to minimize time. The way to do it is, so we know this, that dt is equal to ds, which is a length element, by v. Hence, if we integrate this, so p is equal to ds by v. Now, I want to write this equation, so I will substitute as v of r, and this length element I'll write in terms of, so this is a, so you see there is a symmetry in the z direction, so you are not considering the z direction. If you just consider the, if you just consider a sphere, sorry, a circle, and we can parameterize ds in terms of the polar coordinates. We can also put so ds is nothing but uh, an infinitesimal line element in cylindrical polar coordinates, which is equal to dr square plus r square d theta square, or d phi square plus dz square. Okay. So we have ds is equal to dr square plus, this is a very bad notation, but it's all right. This is not how I should write it, to be honest. This is not how I write it. So from here, I'll write ds as in terms of dr. Well, let me ignore this coordinate. It's just going to be making it difficult only. Let's do it like this only, because it's there's a symmetry in z. This does not depend on z or something. So we can just treat it as a disk and work on it. So for that case, we'll have this as this, ds square as this, and we can write ds is equal to, I will parameterize this in terms of d phi. So dr by d phi plus r square, yeah, plus r square. So this is my ds. Thus, I am writing r as a function of phi. Therefore, t is equal to integral d phi r square plus dr by d phi by v. V is C times R by A plus A minus R by A n. Yeah. That is equal to integral d phi 1 by C R plus A minus R by N. So we have found it. So now we want to minimize P. You can look at this equation and make parallels with the action. So P can be thought of as S, Y can be thought of as T, and then the whole quantity, whatever is inside this quantity, can be thought of as L. So we have L as square root of R square and R prime, R prime square R plus A minus R by N. Now we have to vary the Lagrangian. That is, if we do the variational principle, we are going to get the Euler-Lagrange equation only. And the Euler-Lagrange equation in our case will be of this type actually. Del by dou phi is equal to, sorry, dou by dou r is equal to d by d phi of dou by dou. So this is the equation which you need to solve. So we'll solve that now. Let me take this L. Let me first calculate dou by dou r. This is quite complicated. So we are going to have to differentiate this one first. That is R by minus R by N, and differentiate this was N by plus, we differentiate the lower term, which is N plus A minus N whole square minus N, and differentiate this 1 plus 1 minus N by N square root. This is 1 dou L by dou R prime is going to be just R prime plus square root R square plus R prime square R plus A minus R by N. And we've got to take dd phi of this thing. and we have to write 1 equals 2. This is the Euler's Lagrange equation. And then we have to solve this equation. This is quite a tedious job, but we know the trick. It's not a trick per se. We know that the Hamiltonian in this problem is a constant because this Lagrangian is not an explicit function of phi. That is to say, Lagrangian is not a, so whatever that function is, it's not an explicit function of phi. It does not have phi coordinates explicitly. It depends on phi through r and r prime, but it's not if you consider the trajectory. But Lagrangian itself is not a function of phi. So in this case, we'll have Hamiltonian as a constant. So we are going to find a first order equation in using that identity. It is also called the Beltrami identity. And we are going to use that to find the trajectory now. The way to do it is h, which is a constant, is pr prime minus l. And pr is dou l by dou r prime. R prime minus l. Dou l by dou r prime is nothing but this quantity here. So times r prime, that is square minus l. L is this quantity here. So this is h, and this is supposed to be a constant. This is a constant c. Now I'll find a relation between r prime and r. Like I'll write r prime in terms of r. So I'll rename this constant as minus c. The minus is gone, and I'll take a square after putting this side. So r power 4 by c square by r plus Hello. Uh, Hello, are you there? Hello, Daksh, are you there?
Yes, yes, yes.
Okay, okay. So I was just doing a problem, which is a problem in, the instructor's book also, that the dynamics of classical and quantum fields, his own book. I was doing problem number 13. This is a problem in variational principle. I was starting with this.
Okay.
So, yeah. By the way, do you have any doubts since you have come here?
Mm, No, I couldn't get a chance to go through the book. I just saw the videos only. So
Yeah, yeah,
yeah,
yeah. From the videos only. Do you have any doubt?
no, no, it seems fine.
Yeah, you are fine with this thing, right? Okay,
Yeah,
there is a comment which I want to make. Let me make it after completing this problem. The comment is that he's teaching something in dynamical symmetry, right? So, like, he doesn't describe what a dynamical symmetry is, and I wanted to describe it properly. In his videos, he doesn't do that. He is equal to two square plus prime square. So, first one, four, therefore, you have to solve the equation d5 dr prime. Let me name this constant as k, because c is already used. dr by r. Dr integrating this to integrate this complicated integral to get a result. And this will be your answer. We have to we'll find phi as a function of r, and then we'll invert this, and we will get r as a function of phi, and then uh, we'll find the this thing and the equation. Yeah. Hello, Daksh. Uh, so
yes.
yeah. So this problem 13, I am making a version of my own. Okay, it's not exactly the same. Okay. So what I'm considering is I have no z-axis. I have just this thing, and it can move in any angle. Fine. the light beam. Okay, anyways, forget the book. I was telling about this thing, the symmetries part. When he's discussing the symmetries thing, what he's doing is he's taking this thing as zero, right? So BDS Lagrangian, this is the new coordinates which is related to the original by some continuous transformations is equal to zero, right? And so this we are putting this as zero, right?
Yes,
So
it
this
means
type
the
of
Lagrangian, setting the Lagrangian to be invariant.
yeah, yeah, correct. So the what is the statement of symmetry? Like what is the statement of Noether's theorem? It says that any continuous symmetry of the system will admit some conserved quantity or vice versa. Okay. So when we mean by system, we mean the defining property is the action. It is not the Lagrangian. Well, and the difference between these two things is that the Lagrangian can change by a total derivative term. Okay, even when the Lagrangian changes by a total derivative term, the action doesn't change. Okay, all right. But if the new Lagrangian is the same as old Lagrangian, then this is also the action doesn't change. Okay, so in his derivation, what he is doing is this case. All right. Okay, these kind of symmetries are called kinematic symmetries. These type of symmetries are called dynamical symmetries. Hmm. Now, if so, this statement in his derivation, this equation one, that the Lagrangian does not change under these deformations, means that if you want to write it for dynamical symmetries, you will change this statement as follows. The Lagrangian changes up to a total derivative for dynamical symmetries. And what will this do is, this will just put a term. Okay, this will just put a term. So this after doing some doing some after doing the what do you say the chain rule and yeah, after performing the chain rule and writing using the equation of motion, we get this term, right? d dt is equal to dqs ds. You remember this? Hello, Daksh.
This is
This
the
will
conserved
be
quantity, right?
yeah.
This is the
This
equation.
thing is the conserved quantity. This thing is the conserved quantity if your symmetry is kinematic.
Oh,
Okay. If your symmetry is dynamical, you have to add a term like this because the statement of symmetry is not that the Lagrangian transforms. It is that the Lagrangian does not transform. It is the statement that the action does not transform. So a symmetry means that you perform some coordinate transformations or anything, it's actually related to the coordinate transformation only. If you do something to the trajectory doesn't change, or like uh, the trajectory to will map to a new trajectory, but they are related by some symmetries. Like, you understand what I mean? So
But for like, as an example for dynamical symmetry, showed that Runge line
yeah, yeah, correct,
the
correct.
thing.
You are showing the Runge-Lyons vector, right? I can show you
Mhm.
that the Lagrangian
So
changes. Yeah,
so it
then
was not this quantity. Oh, okay, okay. That part was kind of weak. Like he, he found an alpha to be the conserved quantity or something, right? An
yeah,
angle.
yeah, yeah, yeah. No, what he meant was that he's getting the whole of the vector. He was getting whole of the vector as a conserved quantity. Okay, the whole of the vector is the conserved quantity. But this vector can be written as some magnitude times, say, n
And
cap. All
direction.
right. Yeah, some direction. And this thing, right? This A is nothing but energy,
And
momentum. Yeah.
L
So
angular
something
momentum.
like, yeah, angular momentum. Okay. These were some mixtures of this only. Momentum was there or not? Momentum was not there, I
No,
guess.
no, not that.
Momentum was there. Energy, angular momentum, and energy, angular momentum, and initial conditions, if you
Okay,
want to.
okay,
Okay.
yeah,
X naughts, whatever. Hmm. Times n cap. But this n cap is also, it's also like it's also this thing. It's also fixed.
con-
This is not like r cap. Okay. In the sense, like if you have this orbit, r cap is this. So you're moving like this, then your r cap is pointing in different directions, right? But this n cap is fixed. It's some vector, which is directed to the semi-major axis. Okay. So that is why it's said that he's introducing that angle, which is alpha, but it's this direction of the vector itself which is unchanged. The whole of the quantity is unchanged, right? So he wants to say that this thing has already has got conserved quantities inside it. There's nothing new there. The new information is here in cap, because this is a vector which is just towards one direction only. The direction, if the particle is moving like this, the LRL vector will always be in this direction only. The magnitude may change, but it's always this direction. Okay, that is what he meant. But that is not, that is an example of dynamical symmetry. That is not an example, that is not an explanation of dynamical symmetry. Okay,
Now, what
okay.
I was saying, like in the lecture, I don't remember you add like
Hmm.
writing the time derivative of the that constant term equal to something. Like it was neither equated
Yeah,
to zero or any as a
it was
derivative of any part.
equated to zero. He wrote this, right? This equation, right?
I guess
He was writing this equation, right?
question is yes, yes. For the
Right.
Langer function also equated to zero, right? He didn't use this derivative of f
He
like
didn't use. Ah, no. Wait, wait. There's this confusion. Wait. So, what did he equate to zero? So, he first wrote A. He first wrote A is something. Okay. What was A? I don't remember now. Some triple product, right? L cross
uh, L
R
cross
cross L.
P. Oh.
across P.
P cross
Across
L, P cross L plus
P,
M KR or something else.
P cross L cross R minus M K R cap.
Yeah.
Okay, so this is A. This he gave you this. This is given to you. And what he was doing was he was doing DDT of A and showing you that it is indeed 0. All right. Hmm.
Yes, yes.
But I am saying you something else. I am telling you how to find A.
Oh.
Okay. So let us explain this properly. Okay. Let us take the example of, say, the most easiest example we have is the free particle. I'll try to explain what I mean. Lagrangian is half m x dot square. Okay. So what I want you to do is do this transformation. X goes to some new x prime, which is equal to x plus a. Okay. Does the Lagrangian change? The new Lagrangian is equal to half m x prime. This is x prime dot square. And this is nothing but half m x dot square.
It's not square.
Right? This is the same as the old Lagrangian.
Right.
So this symmetry is called as kinematical symmetry. Because in this case, you checked yourself. This is the check that the Lagrangian minus L plus, if you write something like this, this term is not there. This f is 0. Right?
Yeah.
This f is 0. So this is a kinematical symmetry. When you have a kinematical symmetry, you are going to write this thing, that ds of L of S, whatever he was writing, is equal to 0. Okay. And in this case only, you can find that the momentum is the generator. So how do you find that? You write, this is the, so this is 0 means, according to his derivation, ddt of dou L by dou S times, what was the other term? P, dou L by dou P dot. Sorry, dou L by dou X dot is equal to 0. Okay. That means this is some constant. I'll call this constant as P. Now dou L by dou S. In our case, S is A, okay? Is equal to A, because this is the quantity by which we are doing the deformation of the if you want to say deformation of the Lagrangian. So dou L by dou S is just 1, because dou L by dou A is 1, times dou L by dou X dot is mx dot. So, okay, that means this quantity is mx dot, and ddt of mx dot is equal to 0. Okay. That means mx dot is a constant. Okay. So this is what he says, that this momentum is a constant. In this case, you're saying something like this. All right. This is an example of kinematical symmetry. Now I'll talk to you about some dynamical symmetry. Dynamical symmetry, we want to cook up some dynamical symmetry which is not this LRL vector. I want to find some example. I don't know if I have some example. I'll just check in this book. I should have thought about this. But yeah, let's see. If there is something. Oh, there is something. Okay, this is a very good example. Hmm. So say we make this change. Okay, uh, we make a like non-relativistic boost. So we have something like, but this requires, does this require, oh, this requires some potential. Yeah. So what I'll do is I'll work out a very nice example with you, along with you, to explain my point. And this is a very nice example. Okay. We'll find what we call as Galilean invariance. Hmm. So consider a Lagrangian, which looks like this. Hey, Daksh, if you are there, take notes about this part. Okay, this is a very important thing, and this thing is not explained very properly. And if you
Sure.
have any doubts, do ask. Okay, where RJK is this. So what we will do is we'll find all the symmetries of this Lagrangian. Okay, we'll do step by step. This is a system of particles. Say there are n particles. This is the potential, some potential between them. And this is very general. Look, the potential is some V. And the only thing, the criteria which you want is V should be like this. So you can see from the expression of this V that V should be like this. It already tells you that the distance between two of them is always the same. Okay. Sorry. I'm so sorry. I mean to say, like, yeah, the distance between the two of them is invariant under rotations. Okay. Now the first, you consider this kind of change. R, any Ri is equal to, this is a new coordinate, okay? Ri prime is equal to old Ri plus epsilon some vector A, some vector A. Where epsilon is some infinitesimal parameter. Okay. Now you change you see, does L change? How does L change? You have to find L prime in this case. If you have R as this, then your Ri prime dot is just Ri dot. This part is A is a constant, so this part is 0. Okay. And your Rj minus Rk mod, this is also unchanged because this is constant displacement and it is same for all the R's, Ri's, the I's, all the particles. So this is the same as this. That means your potential is not changing. Your kinetic term is also not changing. That means the new L is the same as old L. All right. So this is an example of kinematical symmetry. Hello. Hello.
Hello. Now can hear
I
you.
think I
I can
lost
hear
my
you.
network.
Mm.
Oh, okay, okay, okay. Wait. I think I lost my network. Just uh, I'm so sorry. Where is it not? Okay. Yeah. So L prime is equal to L, the constant of motion, the whatever he was calling as Q. Okay. So that will be what in this case it will do Rg dot times the generator of this thing. That is delta Ri I am writing. Okay. And delta Ri is nothing but epsilon A. This delta Ri is what he says as dou L by dou A. Dou L by dou epsilon in our case. Okay. Dou L by dou L is dou L by dou S. In our case, the parameter by which we are shifting is epsilon. Okay. So delta Ri is epsilon A. So this dou L by dou Rj is Mj Rj Rj vector dot times this is J vector. Okay. Mj Rj dou L by dou Rj. And there's a summation. Oh, I should have just made this thing. And J should be from 1 to n number of particles now. Right? This is correct. Okay. So delta Rj is actually dou L by dou Ls by dou S. In our case, this is nothing but dou dou Rs plus. Wait, what was the expression again? dqs by qs. I'm so sorry. It's not this is the generator. So dou R by dou X. Dou qs by dou S is equal to dou R by dou S in our case. This is R prime dou S, so dou epsilon in our case. So you get this. So you have summation J. Okay, and this is nothing but momenta. We are just saying the total momenta along the direction wherever you are changing, along the direction of this, along the direction of, uh, along the direction of this RIs that is being conserved. Okay, this is the this is the first Galilean invariant. Galilean invariant. And this says that total momenta is conserved. Okay. Now we'll consider the next variation. The next variation is this. Some x is n cross Rj. Okay. And n is a constant unit vector. So this is the rotation. Now under this rotation, you can show that this remains the same and also this remains the same. It is very easy to show that Rj remains the same because you can think Rj square as a matrix is summation Rj. It is a matrix R1, a column vector, and a row vector. And here, rotations mean nothing but some orthogonal transformations. So there is a matrix M. So your new this thing R prime is equal to some M times R. This I'm calling as R. Therefore, this R transpose M transpose, and from this side M R. The new coordinates will be, so this changes to R prime transpose and R, right? And this is equal to R transpose M transpose M times R. And orthogonal matrix have this property that this is identity. That means this is equal to R times this R. So that means this is equal to Rj dot square. So this means that someone that hello. Hello. Yeah. So we figured out that. So we figured out that this quantity, the kinetic term, doesn't change under rotation. Okay. Similarly, the potential term also, which has got due to this mod, it does not change under rotation. Okay. Because mod means you have got a distance something like this, right? Ri minus rc square, and rotations are you do sum over them. These sorry xi minus xj, xi minus yj. Xy is the components of the ith and jth particle. Okay, xi minus yr. Sorry, whatever. So these kind of distances are not changed by orthogonal transformations. So you see that rotations do not change the potential also. So so what you find is that your kinetic term and also your potential term doesn't change. This means that the new Lagrangian L prime is equal to L. Right. So whatever I have said, you can do the calculation for the infinitesimal version also. You will have something like this. You have this as this, and you'll have to calculate then delta this vector. This is equal to d dt of delta rj vector epsilon. This is a constant vector, so you'll have n cap cross rj dot. Yeah. And as I said earlier, I'm going to show here is when you find the variation of the Lagrangian delta L, you're going to do two derivatives. That is, you're going to do a derivative here. J R H, which is nothing but 2 times R I dot delta R. This is that where J R times delta. So you're going to have something here, and you're going to have similarly in the potential term, you're going to have now you know RG square is 0, and so instead of delta instead of is also 0, so the kinetic part does not change. Okay, anyways, so the conserved quantity, hello, did something over. Okay, okay. I missed this. So the conserved quantity in this case is Q equal to summation J and Ej. This is because this part is dou L by dou Rj dot, not dou L by this is delta Rj. Yeah. Minus oh, I'm so sorry, there is minus this ddtf quantity. In this case, L is equal to L prime, so F is 0. Okay, so there is no term. This term is not there. So you'll have equal to J. Dou L by dou Rj is this is nothing but J, is the momentum, and this term is J is n cross J is n cap cross R vector, and so you'll get you will get, I'll write this as pj sum this thing, and pj something as pj and some vector towards some p vector, okay? P cap cross r vector. So this can be written as, this is a magnitude and this is a the vector component. Pj n cap cross r vector, this I'll call as p vector. Vector something like that. Or, oh, okay, this I will not do. Sorry. This I can just shuffle. I also forgot about this. Nk minus dot j vector cross r cap. R cross j. So this term is conserved. This is nothing but the total angular momentum. Yeah. This is it. Thus the total angular momentum is a constant of motion. Now we'll consider something new, which is this. The change that is by coordinate minus the old coordinate is equal to minus epsilon v times t, where v is a vector and v is a constant vector. Okay. Now delta r vector j dot is equal to ddt of delta rj, and delta and this thing derivative they commute. So this is nothing but rj dot. Oh, what did I do? Oh, sorry. I actually wanted to do this. Minus epsilon v vector t. And this is nothing but minus epsilon v. Therefore, now we are going to see how Lagrangian changes up to first order in epsilon, okay? So you just put it in the Lagrangian, this new thing, r prime and r dot prime, j, j. This is equal to L of rj minus epsilon vt and rj minus epsilon v. Are you here with me? Are you following?
Yes, sir.
So this is the part which I want to focus on, okay? Because this is something which will give you a dynamical symmetry. Huh? Now you just put this in L. You just put it in the Lagrangian which we have. So you are going to find half summation j equal to 1 to n mj. You put rj vector dot minus epsilon v vector square minus v, and v doesn't change, right? V remains the same. whatever we do, we have to do till the first order only. This is nothing but rj square minus 2 epsilon r dot v rj dot dot r v square minus v. You realize why v doesn't change, right? In this case, Daksh?
Yeah, that term would cancel out from basically
Yeah,
distance
yeah,
are the same.
correct. Yeah, yeah. So now in this case, so this part and this part is the original Lagrangian, right? It is Lagrangian with R and R dot. And this part will neglect this because this is epsilon square. We don't want to look at this one. And you have the middle term, which is this times epsilon dot dot v vector. Therefore, the new Lagrangian, which I'll denote as L prime, is equal to old Lagrangian minus something. Now this is a constant vector, this v. So the derivative can be taken out and put it fully here. What I mean to say is you can write this thing as d dt of epsilon is outside rj dot v. With that, therefore L changes as, so there is a function f, there exists a f for which is this, j is equal to 1 to n rj dot v, for which Lagrangian changes as L minus ds by dt. Alright, and this f is there. Okay. Therefore, yeah. Therefore, therefore, what we'll have is the conserved quantity is this. Okay. Conserved quantity is summation j of delta r j minus f. And this is equal to j j not delta r in our case is, what is delta r? V vector t minus f is this can be put together and j v vector, and this is nothing but you take v vector out the dot product, you find rj vector minus dt dt. Hello, you there? So you'll find this as this thing. This is the hello Daksh, you're there.
Yeah.
So this you see, this is a constant of motion. Okay. In this case, this is a constant of motion. Did you know about this?
I haven't done like this, but yeah, you're saying like in the vector, the df by dt is incorporated in that term. That's what you're saying, right?
Yeah, yeah, yeah. The F should be included. Okay. All right. If I do not
Yeah,
include the F, if I do not
yeah,
include the F,
I got, I got what is.
okay, yeah, okay, okay, that's great. So, yeah, so this is an example of dynamical symmetry. Okay, great. So, yeah, so what is the interpretation of this? What is this? So we found this is a constant of motion, but what is this? That is the question which we are interested in. And I'll just do some variable changes. This is this Rj, sum over Rj, I'm going to call it as R vector, and sum over Pj, we are going to call as P, going to call as P. Okay. Mm, yeah. There's the M here, MVP. I missed a M probably somewhere. If it has, I should have an M. I missed an M here. Okay, I missed an M here. There should be M. So F by M is this quantity. Yeah. M is here. No, I know this one here. M is here. This is M here. Now look at this R minus PT P by MT part. And this V, you select a direction here, okay? So what is happening is like Vx times Rx minus Px by Mt plus this thing plus this thing is a constant. So these things individually should be a constant. This is C1, this is C2, this is C3. Hmm. And have you found any trajectory which is like, what is this looks like x minus vt is equal to constant, okay? This term. Yeah, r is the general position I am saying, right? But if you compare this with x minus vt is equal to constant, you are getting this kind of like this can be thought of as this. If you take the position of each particle and just do the same thing for each particle, you are going to say xi minus vt is equal to ci, something like that. Okay. So that means this constant has the interpretation of initial condition. All right. So, do you hear me? Yeah, you guys are there. So, these constants, this thing has the interpretation of initial conditions. Okay. So, you know that the initial conditions, if you have got second order differential equation, you should get which is the Newton's equation, you should get how many constants? You should get two constants, right? You should get two constants. And then they can be put into initial conditions also. Or these initial conditions can be written in terms of energy and all these things, right? Now you have got here, uh, you've got here three initial conditions, for example. You got here three initial conditions, and you found energy and you found the total momentum as well as angular momentum as other constants of motion. Initial conditions three, and you have found what uh, angular momentum and angular momentum are in three directions. So three angular momentum, and what did you find? Momentum in three directions for individual particle. You found three. Okay. So and one more thing is there. So there's one more thing, which is the Hamiltonian. You can say the this is the what is that? This is due to the time invariance because the Lagrangian does not have explicit time dependence. By the way, when you find Hamiltonian, okay, this F will be nothing but H. Sorry, this F will be nothing but L. And then you define, and this delta R J will be nothing but R dot. So when you find Hamiltonian, when you want to find the symmetry with respect to the time, with respect to time translations, you're going to find that your F will be L, delta R will be delta R dot will be R dot, and thus your conserved quantity with respect to time translations, which I'm giving in this, which we also call as Hamiltonian, will be Ej dot Rj dot minus L. This you can take as an exercise, okay? You do the explicit change of time as we have done here in this case. What you're going to have to do is you take L and you think that Rj is a function of time. Do the time translation, say epsilon A, and in first order, show that the Lagrangian changes as Lagrangian plus dou L by dou T. This will be the new Lagrangian. You can show this. So there are 10 Galilean invariants, which is the one is the total energy plus three are the momentums, linear momentums, three are the angular momentums, and three are the initial conditions. These are 10 Galilean invariants. And one of these three, which is the initial condition, is an example of dynamical symmetry. This is also an example, the Hamiltonian dynamical symmetry. These two, which is the momentum and the angular momentum, are examples of dynamatical symmetry. Okay, so I'm done with the Galilean invariance. This is what I wanted to say. Do you have any doubts or any questions? Or had you done this earlier? No one? Yeah, you can say.
No doubts. Like I haven't done this earlier, but yeah, it seems
Okay. Now, do you want to go over LRL vector? The way he has done is a very like it's not like the way we want to think about it. First, what we should do, how we want to think about is like this. Okay, given an action, find so I have been given an action. Okay, action I have. The first thing to do is to look for symmetries, that is continuous symmetries. What this means is some transformations, coordinate transformations, leaving S unchanged. Once you know this, directly apply, yeah, leaving S unchanged. The second thing, S unchanged, yeah. So the second thing is to figure out if it leaves S unchanged means L unchanged up to a total derivative and to figure out the total derivative. The third is to just apply the formula, which is this. Dou Ly, that is, I'll directly write it, which is Pj, summation over J, if there are J independent particles or something like that, times the generator of the transformation. Generator of transformation is something which I am writing as delta Rj. What this means is that the transformations, whatever you are doing, new transformations, R prime is equal to R plus something, any f of x, f of r or anything, you delta R prime, delta R is nothing but with a epsilon parameter. Okay, this is the deformation parameter. This will tell you how to deform. You can put this inside and call this new function as g of r, but this is not a big deal. But if you put the deformation parameter intact, you will it will be helpful for you. You will not get confused with notations and all these things. Delta r is equal to epsilon f r. Okay. This is the generator minus f. That's it. Whenever you find any action, do this prescription to find symmetries. You don't have to think anything else. Hmm. But what has happened is like he has, in our case, what he has done is he has gone like this. He has gone the other way. He has given us A, he has given us A, and then he has showed that dA by dt is 0. So he has given us Q. In our case, it's like this is Q. dQ by dt is 0. Okay, now we'll come from the other way. And this is a bit big calculation, and I'll see how much I can do. I hope I'll be done in 20 minutes. So we have the Lagrangian as, so you want to learn this method? No, you want to learn this way? Or I can go to some new problem also. Uh, no, no comments, no nothing. Okay, anyways, okay, let's continue.
excuse me.
Yeah.
Can you go a
Hmm.
page back?
Mm. Which part?
No,
This?
the final one. This delta R, right? Del
Yeah.
R. Is it epsilon FR or F of R? Like, it,
Well, the yeah. There is this small thing here. Okay, so it depends on how you write it. So I also get confused in sometimes in notation. Whenever you write it here, okay, you write f of r, but delta r is this minus this. If you want to put a epsilon downside, it's fine. But you should remember this that it is nothing but del r by del of the deformation parameter. Okay. So whatever you put here, no, this is actually this. Okay. Okay. I'm confusing you. So forget about this. Okay. This is fine.
uh,
Okay. This is better. Okay. But delta r, I mean to say is delta r is this only. Delta r is the change minus the difference.
R prime minus R.
Yeah. Mm. No, 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 no. Okay, that is correct. Actually, in books, it is r prime minus r. I want to make this and this consistent. Okay, I want to make the notation consistent. I will define delta r as like this. This is the definition. Epsilon, and yeah, this is how I want to define. If I use this definition, will there be any problem or what?
No, but again, then there won't be an epsilon in the this one, right? Delta
There would,
delta R would be
yeah. The delta r would be this thing.
F of.
No, I want to see if there will be a problem somewhere else here or something like that. Okay, I don't think so. There will be any problem. This is not a very big deal, also. Okay, but remember, this is what it is there. Okay. Mm, yeah. Okay. Let me put the notation in the container for all. Mm. So from the books which I'm doing or which I had done, there's this delta R always has got this epsilon. Okay, so that is why I want to fix this thing right now so that later on you don't want to. Mm. Okay, anyways, you can think of this in other way. If you put delta R here, and even if that has got epsilon and F itself has got an epsilon, you can put that epsilon as Q by epsilon. You call this as a new constant, something, say, constant J. That is also an acceptable answer. What I mean to say is that the epsilon should always come as an overall constant, then it doesn't matter. Hmm. Because there's always this notational problem. Some books, uh, they write this epsilon, but in the last answer, you won't have this epsilon in the constant because you can always put that as you can always do this kind of thing. Okay. Is it cool?
Yeah, yeah, it's fine.
It's fine, right? Okay. Now let's do this. So I have this Lagrangian, the central force Lagrangian. Now, what you're going to do is directly we are going to do this is the symmetry transformation. Del r vector is a. This is some a vector which is constant and cross r vector dot cross r vector plus r vector cross a vector. Okay, this is the symmetry transformation which we want to do in R. Hmm. This can also be written as this. I'm directly copying from some place there in Wikipedia. Minus a vector dot. Okay, under this symmetry transformation, we want to find out how the L changes. All right, that is our job. So you just have to follow this prescription. So the first thing is that the continuous, what are the coordinate transfer leaving S unchanged, right? I am telling you that this does it. This thing does not change S. The way to see it is you just calculate, you just calculate L. You'll find that the new L prime should be equal to L plus df by dt. Now we will do this, okay? And to do this, we have to figure out delta r vector dot. So quickly do this calculation. What you find important? This is important. Are you calculating along with me, guys? Are you doing this calculation? You just have to take the time derivative of this one. Let me do it. 2 a vector dot r dot r dot plus 2 a vector dot r double dot minus a vector dot r double dot minus a vector dot r dot minus r dot square a minus a vector dot r double dot into this. This is one. This goes like this. Minus a vector dot is there any term? 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. It's 2. Yeah, now put this in L. This is going to be a very long calculation now. Okay. So let me do till 8 minutes and let's see where we reach. So L prime is equal to half n r dot square is 2 r dot square is r plus that one is equal to r plus r dot r dot plus r dot square plus c by r plus r after this plus I will do plus and scale generate and till the DBT delta DBT is large. That is good. You can directly have to do r dot r is equal to yes you will to minus this is such a big information. Well, hello, are you guys there?
Yes,
Yeah, can you guys do this after this? It's really turning out to be big. You have to take the dot product of all the terms and you have to show that this looks like a term called DDT. This looks like, I'll write the answer for you. Huh? So what you get is L prime is equal to L plus DDT M a vector dot r vector is r dot square, r vector dot square minus a dot r dot, a dot r dot, these are all vectors, plus a dot r vector, a, hmm. So the point which I want to make is this: the conserved thing is this is the Q is the conserved quantity. So the P vector times delta R vector minus F. F is this thing is equal to this is P vector dot delta R is, yeah, Daksh, you have something to say?
No, no.
Were you trying the calculation along with me?
I'm noting down what you write.
Uh-huh.
I'm noting down what you're writing, like the results we wanted to get, right?
Yeah,
Now
yeah.
you're writing the result.
So I'm directly writing the result which you'll get. This is what you should get. Okay. This thing is what you should get. So you do this now. You'll do this variation, right? Okay. There should be r plus delta r also. You have to do the binomial expansion and up to order epsilon. Okay. Up to order a in this case.
That's right.
And some terms will cancel. This will be a bit tedious calculation. Huh. But the answer which you'll get is this. This is the answer. Hmm. So I actually wanted to get to this point, okay, where I want to write the conserved vector. You're going to see that if you use this in this formula, you're going to see that this is nothing but the Laplace Runge vector. So this is E dot vector minus infinity. Not E delta R is this is or the whole of this term can be written as A dot P cross R cross P. Okay. So that there is some number in time here, and this is the LRL vector. Hmm. So the thing is that in the case of LRL vector, so the first thing is that even if you have kappa positive or negative, you're going to get this thing as a constant. It doesn't matter. But when you have this thing, the sign is negative here, you're going to get an ellipse for some energy. And if you've got the sun here and the planet is here, and if it is moving,